All right, thanks, Marcus. All right, let's talk 3D printer resolution and accuracy. So, what determines an accurate, detailed print? Right? What would allow you to say print a part for like this engine carburetor, or to print a super detailed sculptural bust, say of Thanos here, which I like to think is probably how you'll look if you don't get an accurate part, or say if your printer is not meeting your expectations, to which then you will just snap that printer right out of existence. Now, what determines this is what I like to consider this web. You've got accuracy here at the pinnacle, and you've got all these different factors that tie into it. So you've got your printer's resolution, which a lot of people mistake for accuracy. You've got your printer layer height, the layer height at which you're printing your part, the spot diameter at which you're either curing that material or extruding and printing that part. You've got the type of printer that you're using, the material for that type of printer, and the tolerance that you're having to model in CAD to kind of counteract and work with that accuracy. So all these different factors are interconnected in this web. And what we're going to do is we're going to start with resolution and kind of work our way clockwise, just defining them and trying to understand what each of these are. So let's start with resolution. I think the best way to start talking about resolution is to start at a point that we all can understand. And let's look at like screen or monitor resolution. So because we're looking at stuff in the 2D world, we've simply just got to worry about two axes. We've got our y-axis vertical, we got our x-axis horizontal. And whenever we're talking about screen resolution, these are all figures that we're probably familiar with. So 480p is pretty low resolution, going up to 720p and 1080p. These are like HD resolutions, up to 4K, which is like ultra high definition. But what do these numbers actually represent? Well, they're simply pixel areas. So on a 16 by 9 widescreen aspect ratio, which is your typical screen size, you're looking at, say for 480p, you're looking at 480 pixels vertical by 640 pixels that are horizontal. So that's what makes up that area, that 480 pixel area. And so as you move up the chain into higher and higher resolutions, you can see that our number of pixels, our number of little dots and boxes all across the screen are increasing. Up to 1080 and up to 4K Ultra, which has almost 4,000 pixels in the horizontal. That's actually where the 4K term comes from. And so we're all familiar that as you get into that lower resolution, as you get into fewer and fewer pixels, the screen, the quality of that image goes way down. Okay, they often call it potato quality, right? So that's something at like 240p or less. And then when you get into like your HD, right, obviously you've got a lot more pixels. It's making up a much finer image quality. So when you look at stuff in the 3D world, you've got to take into account a third axis. We looked at the XY. Now we got to consider the Z-axis. Now you can look at the print bed as being synonymous with the screen resolution. Essentially, you've got all these little boxes that can make up that print bed. And with the Z-axis, imagine like just a single stack of boxes going straight up. Now, we're talking 3D printer, so we got to talk about a print head. And I'm just going to talk generally, just in terms of FFF printers. So we've got a print head, we got a nozzle. And what you'll find is in the screen up on the, or this graphic here at the top, we're looking at the print bed. Imagine the print bed see-through, and we're looking up through it at the bottom of the nozzle. Okay, the very tip. And you can imagine that each one of these boxes is the movement of that print head. And the nozzle is centered in each box. And that is what defines that movement there. And similarly, with the Z-axis, just stepping up, one block represents one step at a time. Represents a single solitary movement, moving up. Now imagine we were to take this volume and we were to increase the number of boxes. Now what you're looking at is a much finer, precise movement of that print head. And what that's going to do is it's going to translate into a much finer, resolute part. Now, what controls this? What controls these fine steps, these movements? Well, stepper motors do. So if you look at an FFF printer, say like a roughly Core XY type design, like this Markforged desktop printer, you'll see that we have two motors. I've outlined them with those two yellow boxes. And those are controlling the belt movements. And that's actually what's moving that print head across the XY plane. And similarly, right, we've got that third axis we talked about, that Z-axis. We have a motor that's controlling the movement of that print bed up and down. Now, with an SLA printer, we also have stepper motors. We have a stepper motor that moves that light processing unit across the X-axis. That's that horizontal lead screw we see there. There's motors inside the LPU that move the laser in the Y-axis. And then there's a stepper motor that moves that bed up and down on the Z-axis. And just to give you a better understanding of what that stepper motor action looks like, you're essentially powering magnets at 4 quadrants, and it's moving a centralized shaft in steps to each one of those 4 points. Now, how precise those steps are, that is what's going to translate into how high your resolution is going to be on your printer and on your part. Now, I'm going to throw a little bit of a curveball at you guys with a technology called MSLA, masked stereolithography. So you're taking the stereolithography technology where you're curing photopolymer resins, but now what you're doing is you're actually using a screen to mask with pixels areas off to let UV light in selective areas. Now what you'll find is you'll see advertisements for 4K MSLA printers, 8K MSLA printers, and what that terminology means is that's the resolution of that screen. So here you're combining kind of that screen resolution that we talked about at the beginning, and you're combining it with the 3-axis that's typical of 3D printers. Now, one thing you can use to examine resolution is by simply CADing features on the vertical walls of your part. So simply an emboss and or a recess, and then printing it. So on this FFF print job that we did, we printed a 0.2 millimeter emboss and recess, and we saw that the printer and the slicer were able to recognize that feature and print it successfully. And so we took it one step down, went to a 0.1 millimeter emboss and recess, and that also printed well. But when you start going below that, the slicer has a harder time detecting that because it knows the printer is going to have a hard time detecting that, just knowing on the hardware of the stepper motors themselves. Okay, so we saw resolution. Let's take another factor and look at layer height. Now we remember this graphic. Layer height simply is just Z-axis resolution. So now you can start to see how these terms interconnect. So we talked about having less number of steps in the vertical direction versus more number of steps in the vertical direction. So if you were to take fewer steps in the vertical direction, what you're going to see is layer lines that are more defined. So the part on the left was printed at 0.2 millimeter layer height. The part on the right was printed at 0.1 millimeter layer height. So we had a smaller layer height. We don't see those layer lines quite as much. And to give you a better illustration of this, let's take this part and look at the profile. Look at that side view. And what you'll find is that when you split up that profile into steps, say at 0.2 millimeter layer heights, you can see those steps don't quite represent that spline curve. Whereas if you were to take that layer height and dumb it down by half to 0.1 millimeters, now you can see these finer steps are more accurately representing that very gradual spline curve. Now, layer height is actually controlled by you. It's controlled by you in the slicer. So you take that CAD model, you export it as an STL or an OBJ or a 3MF, you load it into your CAD or into your slicer rather, and you predefine these layer heights. So with Markforged Eiger and with Formlabs Preform, depending on the material you're using, these layer heights are predefined and you have an option to select certain ones. And then with more open source slicers like Slick 3R, Prusa Slicer, Ultimaker Cura, you're actually able to enter in figures manually. Now, another thing to consider whenever you're going in to select that layer height is to consider the z-axis height of your part. So imagine we're looking at this profile again, and the height of this part is 17.33 millimeters, kind of an uneven value. If we were to take this and print it at a pretty tall layer height, like that 0.2 millimeters, what you'll find is that 0.2 doesn't quite go evenly into 17.33. And so what's going to do is it's going to stop shy of that height that's modeled in CAD. Now, if we were to take that same part and dumb down that layer height to that 0.1, what you're going to find is we're going to get much closer to that height there. So an easy way to think about this is just simply dividing that height by your layer height. So what we can see is that by printing it at 0.1 millimeter layer heights, we're getting much closer to an evenly divisible value. Alright, so we kind of saw how resolution and layer height are interconnected. Now let's take another look at another factor, that is spot diameter. Now with FFF printers, that spot diameter is controlled by our nozzle. And if we take that nozzle and we cut it in half, you can see our nozzle diameter is 0.4 millimeters. That's like a standard nozzle diameter size. And imagine we're printing it, about a layer height of 0.2 millimeters. Well, that nozzle diameter actually controls your layer height. And that's because we want to keep our layer heights within 25 to 75% of our nozzle diameter. The reason being is if we try to drop down below 25%, we have a lot of back pressure forcing up against the extruder. That's pretty bad for our system and can result in some pretty ugly prints. Whereas if we try to step above 75%, that's where you run the risk of layer delamination. That 45-degree rule to avoid support material doesn't really hold up as much. So with a 0.4 millimeter nozzle, we want to keep our layer heights within like 0.1 to 0.3 millimeters. And so that's what that kind of looks like in regards to a cross-sectional layer of a 3D printed part there. Now with resin printers, we're using lasers. We're not actually extruding plastic material through a nozzle. We're using lasers, and that means we can have a much smaller spot diameter. So a typical laser diameter, say on like a Formlabs SLA printer, is less than 0.1 millimeters. It's very small. And that means that we can get some pretty fine details. Now the SLS printers, which are powder-based, they have lasers as well, but they use a slightly larger laser just because now you're having to use a laser to sinter powder together, actually like just prior to melting that powder. So you have to have a higher power laser. It means that laser diameter is a little bit larger. So at 0.25 millimeters, which is the laser diameter of, say, like a Fuse SLS printer from Formlabs, you can see that kind of hovers right in between the 0.4 millimeter nozzle diameter from an FFF printer versus that 0.085 millimeter laser diameter from an SLA printer. And that results in SLS kind of falling in between FFF and SLA just from like a property standpoint. And that spot diameter has an impact on the size of the features we can print. So if we look at this 2D schematic, take note that this feature, this thin-walled feature, I'll just mouse over it here, that's 0.5 millimeters thick. Now imagine we have these two different orientations that we can print this part. Okay, so there's our 3D schematic. If I go to print these, one is going to print successfully, one will not. Now, this one here at the top was printed against the print bed. So that large square face is on that print bed. And the orientation at the bottom is with that thinner rectangular face on the print bed. Now, why did the top one not print correctly? It's because that nozzle diameter is 0.4 millimeters, and that feature is only 0.5. And typically that nozzle diameter, of 0.4 millimeters, your bead width, your extrusion width is going to be somewhere between like 0.4 and 0.5 millimeters. So in this case, the slicer didn't recognize that feature. It said that's not going to be possible. We don't have the we're not confident that print is going to print successfully. So no feature was recognized by the slicer. Now by printing it vertically, each of those grate lines being 0.5 millimeters, printing at 0.1 millimeters means that each one of those gray lines has 5 layers. So it's going to print much more successfully. So that's where you can see how Z-axis resolution actually is more accurate, a little bit more predefined versus the XY. And we'll see a little bit more in detail why that's the case. So here we saw resolution and layer height being tied. We saw how spot diameter, the size of the spot, whether it's the laser or the nozzle diameter you're using, can predefine that layer height. Now let's go into printer type. So we've looked at 3 different printer technologies. We looked at the extrusion-based FFF, we've looked at the powder-based SLS and binder jetting, and we looked at the resin-based SLA, MSLA, and DLP. And the reason they're oriented this way from left to right is because as we move from left to right, we get finer and finer detail. And you can see this in this chest rook piece. So on the left, bottom left, we have this chest rook printed on an FFF printer. You can see the layer lines are a little bit more visible, and some of the features may not have printed quite as well. You can see some stringing, that sort of thing. But as we move up to the next stage, the SLS printer, the surface finish is maybe a little bit rough, but the layer lines are a little harder to see. And then as you move up to the SLA, it almost looks injection molded. So there, the layer lines are virtually invisible, and you can see lines are much crisper, the details are much sharper. Now, let's look at the material that you're going to print with. And this has some relation to that printer type. So if you look at, say, the 2 predominant 3D printing materials for FFF printers, you've got PLA and you've got PETG. So with PLA, you can run that cooling fan at 100%, and that allows you to essentially harden that material as soon as it's extruded from the nozzle. That allows you to bridge really well, allows you to get very fine features, versus PETG, which is a lot stringier and gummier, and you can't run that print fan quite as high, so certain finer details don't print quite as well. Now if we look at the resin technology from Formlabs, they have a material called Elastic 50A, and as you imagine, it's a flexible material. And as such, it doesn't handle finer details quite as well, just given its elastic nature. Versus like your standard gray material, which is absolutely incredibly accurate and is really good for prototyping, especially of like super high detailed parts and doing things like injection molding where you don't want any layer lines. You need to capture all those really fine details when you actually go to mold and cast that part. Now you can even step further back, and we looked at the different printer technologies. If you needed to print something like I mentioned, like an injection mold, and it needs to capture very intricate details, that's where you might say, well, I need to choose a more, a resin-based material, and that would then in turn push me to a resin-based printer, like an SLA printer. Versus, hey, I just need something a little bit more basic. The, surface finish doesn't need to be quite as accurate. I really need to go for something that's very strong. That's where like a composite technology like Markforged would do you well. Now, we're going to talk about tolerance, and tolerance and accuracy really play off each other. Now, the ideal case is we basically forget tolerance entirely, which you can pretty much do if you're going to, say, wire EDM apart. That's what you see in this graphic here. But the reality is not so kind. We actually have to model in gaps, realistic gaps, so that mating parts will fit together nicely. Now, a good way to visualize tolerance is simply to look at like a hole in a shaft. So that's like this, just cut in half. You'll see that the hole in the shaft, they're going to have some deviations. That's just in regards to that printer accuracy, so that's a little bit of foreshadowing to what we're going to talk about here in a minute. And then you've got the CAD dimensions between that hole diameter and the shaft diameter. And to account for these deviations, you got to set that using tolerance. So on that part that we saw in that GIF earlier, you see I modeled a 0.2 millimeter clearance between those two features so that they will slot together. Now, one thing I'd like to differentiate is tolerance versus offset. So tolerance, you actually have to take into account the dimensions on both sides. So for instance, a 10 millimeter hole and a 9mm shaft has a 1mm tolerance because we got 0.5 millimeters on both sides. However, an offset, I think, is an easier way to think about tolerancing. And the reason being is because offset is a CAD term. And it's very easy to make the mistake of thinking you've put in, oh, I need a tolerance of 0.5 and accidentally CADing in an offset of 0.5. And then you've got something that you're not really happy with when you go to manufacture it. So it's a little bit easier to think about things in terms of offsets. Now people ask me, Joe, I don't know the tolerance of my printer. I don't know what tolerance I need to model into CAD. What should I do? And what I always recommend is to print a unit test. Now unit tests vary a little bit based on the printer technology. So with FFF printers, you've got two different types that you can use. You've got separate prints where you actually model and print objects and bodies separately that then fit together after the fact. So say like this pegboard jig that we modeled. We've got the square peg, we got the round peg, we got the corresponding slots on this pegboard. And the numbers there that are in the center of that board represent offsets. So you've got a 0mm offset all the way up to a 0.5mm offset, which, if you recall, that's a 1mm tolerance. So what you can do is you can slot those in and you can figure out, okay, this is roughly the press fit for my printer, this is the close fit for my printer, and this is a loose fit with like zero friction. And so typically what you'll find with most FFF printers kind of fluctuates in this range. You've got like 0 to 0.05mm press fit, 0.05 to 0.1mm offset for a close fit, and then anything above 0.1mm is going to be more of a loose fit. Now the alternative is a print in place. So this is where you're actually modifying moving bodies in situ so that after printing they cannot be pulled apart. And that's really great because, obviously with, if you don't have access to hardware, that sort of thing, print in place can be a great application. But what you'll notice is that the print in place offsets are higher than our offsets for separate prints. And that's just the nature of the technology. So what you can do is you can go around and you can swivel each one of these spools, and you can figure out, hey, this is where it's a little bit tight there. This one didn't, this one is totally immobile, it's fused, and these ones are really loose. So unit tests are a great thing to have on your desk while you're CADing, and you can go and say, okay, this is exactly what I need to model in. Now with SLA, typically you mostly just see separate prints, so a very similar application here with that pegboard, just a shaft and a hole, and running through each one. Each one is sized a little bit differently. And so what you find is that with separate prints, look at that loose fit. That loose fit is anything above 0.05mm is going to give a loose fit. So that kind of feeds back into that printer type. We saw back here that a loose fit on an FFF printer is like anything above 0.1. So you can see that our SLA printers are getting these offsets much tighter, and that's just the nature of that printer technology. That printer type can produce parts within a tighter range. Now the alternative to the print-in-place tests, which aren't typically recommended for SLA printers just because it can be difficult to remove uncured resin from some of the tight spaces. So then when you go to cure it, you end up fusing that part anyway. Typically what you'll see with SLA prints is doing like kind of these feature blocks where you've got bridging and overhang tests and thin-walled features and posts and holes. Those are really great to also keep at your desk because you can take a pair of calipers and say, hey, what size was this feature? It was 0.5mm thin. So then, okay, that I know that will successfully print when I go to actually model that in a CAD and then print it in turn. And one thing to note is that SLS kind of falls somewhere in between SLA and FFF. Here you can see this Rubik's Cube that was designed by the Formlabs team and printed on their Fuse 1 SLS printer. And it has a variety of different unit tests that make up each facet of the cube. All right, now we've reached the pinnacle. We've gone through all 6 of these. Let's touch on accuracy. What is it? Essentially, on its simplest level, accuracy is just how your part dimensionally compares from reality to theoretically. So reality being your actual part in hand, measuring with calipers, versus what that measurement is in the CAD model. Great way to measure accuracy is simply just print a number of blocks. Take a block, typically like 20 millimeters cubed, print them one by one in succession, and go and measure across the X, Y, and Z axis. And plot that data on a histogram, and that will give you a great idea what kind of accuracy you're looking at for your printer. So we did that with our Markforged Mark II, so that's their desktop line of printer. And what we saw was, now bear in mind this range is 0.5 millimeters, so 19.8 to 20.3. That block nominal was 20 millimeters. And what we saw was the X tended to print slightly oversized by no more than like 0.25 millimeters. And the reason being is because that X is pretty wide. It's like 320 millimeters versus the Y, which is less than half that. As you can see, the Y, as a result, tends to float a little bit closer to nominal, a little bit oversized, but by no more than like 0.15 millimeters. And then the Z axis, you can see, is much closer to nominal. And that kind of feeds back to the Z axis being able to print a lot finer and a lot finer resolution, a lot finer accuracy than these other two axes, right? We saw that with that part with the thin 0.5 millimeter grate lines. And you can see that Z axis also is tighter. It doesn't really exceed anything more than like 0.1 millimeters. And so just generally speaking, in terms of an FFF printer, just like what we saw from our data, that XY axis, you're going to see an accuracy range of like plus minus 0.25 millimeters, and a Z-axis of like plus minus 0.1 millimeters. Versus like SLA, you're going to see an XY axis and a Z-axis of about plus minus 0.1. That's straight from Formlabs data, where they found, they get almost unified accuracy across all three axes. And again, SLS floats right somewhere in between. Also, with Formlabs testing, they tested with a variety of different materials, and they found that depending on the material they used, they saw different accuracy. So again, that feeds back to how accuracy and material are tied together. So we've covered all 7 of these topics, but there are 2 other topics I wanted to talk about, but I saved them to the end because they're highly dependent. And that is the maintenance that's being done on the printer, the condition the printer is in, as well as the detailed aspects of your part, the geometry, and that sort of thing. So with looking at printer maintenance on, say, an FFF printer, the things you want to consider are like your belt tension. Okay, the ability to move, right? That stepper motor's got to move that print head in a very precise manner. So you want to make sure those belts are tightened within the proper range. Too loose and you can run, especially with fast jerking movements, you can actually cause steps to be lost. You can actually cause shifting on your part. So you want to make sure that that tension is within the proper range. Markforged has a really great system for determining the proper belt tension simply using frequencies. So it's a simple tuning app like you use for instruments, like especially stringed instruments. There's a tuning app you download. You simply plug the belt like a guitar string, and it'll register that hertz frequency. And Markforged on their support guide has the proper range that you want to keep these belts in between. You also want to consider your how level your print bed is. So whether you have a shim-based system like the Markforged desktop, or a laser-based system like the industrial, or a mesh bed leveling system, you want to keep that print bed level. As you imagine, an off-kiltered level print bed is going to cause an off-kiltered part. You also want to make sure your print bed's clean. So in this case, this print bed is not so clean. With Markforged printer, we use a glue stick to allow the parts to adhere to the bed. But as you build up, layers and layers of glue over time, it can affect the ability for that first layer to go down, which can cause subsequent layers to be off and can affect the overall dimensions of your part. You also want to make sure that purge lines are being printed. So on a Bowden tube system, especially if you're printing with hygroscopic materials, which are materials that absorb moisture from the atmosphere and the environment, you want to make sure you're running those purge lines, because what it's doing is it is purging and exhausting any compromised material. And that way, when you actually go to print your physical part, you're using uncompromised material. Now with SLA and SLS, you can join these together because Formlabs told me that 80 to 90% of print failures are a result of dirty optics. So you want to make sure your optical window is clean, your tank film is clean, the optical set, if you have a fused SLS printer, you want to make sure all these are clean so that the laser can easily pass through without any kind of occlusion. Speaking of occlusion, you want to make sure you do not have any cured resin rather in your vat of uncured resin. So this is definitely a bad situation. You want to make sure that's cleaned out, because again, it's an obstacle between the laser and your actual part. Finally, with SLS printers, it's very important that you maintain thermal uniformity inside the print enclosure. So Formlabs recommends only taking out your build platform when the print enclosure has fallen below 45 degrees Celsius. If you try to pull it out sooner, you run the risk of uneven cooling on your part, which can result in the part warping, and as you might imagine, that's going to affect the dimensional accuracy. The final part is talking about part details, the actual geometric aspects of the part, as well as the file saving aspects. So if you take this bracket, for instance, you'll notice that we have holes that are printed in the XY plane, as well as holes printed vertically in, say, the X, Z, or the YZ plane. Now, holes always print more accurately in this orientation. So that's a situation where these type holes you can measure with calipers and get very close to your CAD model's dimensions versus these holes here. And also support material sometimes can affect the dimensional accuracy of the part, which with SLA printers, with the truss style supports, having to snip those off, you're going to have to sand that down because those pips are going to obviously affect the dimensional accuracy of the part, which can be one of those things you can control in the slicer. You can actually set the touch point, which is the touch point is the interface between the support and the part itself. You can actually take that touch point and you can control the size. And by doing so, if you have a really small feature, that might be something where you'd want to adjust that touch point smaller so that when you go to snip it off, it's not going to really mess up that small feature. Now, with SLS, no support material is actually generated. The powder itself and the bed is the support material. So with that Rubik's Cube that we saw earlier, you can get really complex geometries without having to remove any support material and messing things up. So if you have very complex geometric parts, SLS is a very great technology for that. You'll see companies like Zinger out in California that makes hybrid cars. They use that topology optimization, and they have really crazy complex suspension components that look very organic, and they use SLS technology to print those for that very reason. Now, saving your part can have an impact on the dimensional accuracy. So if you choose file saving parameters that generate a very low poly model, obviously you're going to see less dimensional accuracy versus one that has been saved so that there's very few facets visible on the actual part. And so what I've seen recommended is, one thing, you want to keep your file below 20 megabytes if you're saving it as an STL. And when you go to save the STL, you can open an options window on most CAD softwares. And from there, you can modify chordal tolerance and angular tolerance. And minimal side length is kind of an optional thing. The chordal and the angular are the most critical. And you just want to make sure that your file size is less than 20 megabytes. And so that's just a little screenshot there from saving an STL out of SolidWorks. When you go to save it, you'll have that File Explorer window pop up. When you generate, or when you select the STL from the list of file options, you'll see an options button that you can click, and that'll generate this window where you can set everything. So here I've set that tolerance to 0.1, the angular tolerance to 1 degree, and I've made sure to select that as a binary STL. And that's going to generate a very modestly sized, but still, dimensionally accurate and representative 3D part. Well, that's all from me. Thanks for listening. I guess I'll hand it over to Marcus, and we'll answer any questions that you guys have.